Okay, hello everybody and welcome to Chloethedev Unfiltered. I am just getting this video started because I was supposed to go through this paper a couple days ago, I think, maybe yesterday, but I just keep getting busy and things keep happening, and if I don't get this paper done live now, it's not going to happen, and I'm going to have to read it on my phone or something like that, and that won't be as fun. So I'm just going to pop in, get started. So this is a paper written, I guess, last changed 16 days ago in HackMD, written by Vitalik to the best of my understanding. I guess I'll sign into my HackMD so that I could, I could like it. I could either bookmark it as well. I'll probably end up bookmarking it so that I can keep up to date with reading it again later on and seeing how it changes. Either way, I'm going to get started reading it. I will not understand all of it, I'm sure, but the point is to start getting more familiarized with Phase 1 because I've been focusing so much on Phase 0, but now Phase 0 is about to launch. Now it's probably a good time for me to start looking at Phase 1 and what that's supposed to look like. So, the purpose of this document is to describe in more detail a proposal for how Phase 1 can be structured based on a data availability focused approach. I think so far so good. I think data availability is super important, and I think focusing on and ensuring that the data is available for whatever nodes or whatever shard you're on or whatever you're personally working with is what's going to be important to most people using Ethereum 2. So the main addition to the beacon chain will be a vector of shard data header objects, one for each shard. So in Phase 1, we're going to be adding in shards to the blockchain, but I don't think we're adding in any transactions, just state. I think no transactions between accounts, but just state changes, I think. I can't remember. A shard data header is a small object which represents a large amount of underlying data, roughly 0 to 112 gigabytes in size. Oh, okay, glad to have my glasses back on. A block is only valid if the underlying data in the shard data header points to is available. If the underlying data that the shard data header points to is available. Okay, so a block is only valid if the underlying data is available. That is, it has been published to the network and anyone can download it, okay? However, to preserve scalability, clients will not try to download the full underlying data of every shard data header to verify the block. Instead, they will verify that the data is available using an indirect technique called data availability sampling. So the point of this is that a block is only valid if all the data for the block is there. That makes sense. But instead of verifying that all the data is there by downloading all the data, we're going to verify all the data is there using a technique called data availability sampling, which is, I guess, what this whole article is about, or paper, report, I don't even know. So parameters. So the parameters, you're going to have shard count. So we're going to have, looking at 64 shards still apparently. Points per sample, 8. So this is the number of block data header objects per block. The points per sample is the number of evaluations of the polynomial in each chunk that gets sampled. So it looks like when I was going through the Nightshade paper for Near, where we're talking about chunks, and now the reason I went to that as well to help me with my understanding of sharding, and it seems like in this sharding as well, we have a different use case of the same word, chunks, and so I wonder if we're having the same definition for a chunk here as well. But these are the evaluations of the polynomial in each chunk that gets sampled. We group a few evaluations together for efficiency reasons. Okay, so you're not evaluating everything, I guess. The modulus that is used for arithmetic operations, the polynomial construction and evaluation are all done in modular arithmetic. So I guess obviously if I later on could dig into that there. With this modulus, we have around 31.7 bytes per evaluation. Samples per block is 4,096. So the number of samples in a block that when that block is extended, so the amount of actual data is at most half this. Okay. Fast shuffling samples. The number of samples indicates, the number of sample indices that adjust quickly. Slow shuffling indices. 4, the number of sample indices that adjust slowly, and slow shuffling period. So these are the slots between slot reshuffling. So 4,096 slots between slot reshuffle, and 4,096 is the number of samples in a block when that block is extended. So, okay. I'm not going to act like I understood what all of those numbers and all those words mean in relation to phase 1. But that's the point, right? I read through this once. Hopefully I understand it a bit better. And then as I read the updates, as I read through the notes, as I read through other papers on data availability sampling, hopefully I'll understand it more each time I go through it. Usually I understand it a lot better when I watch conference talks on a topic. So I'm really excited for like FCC this year and like DevCon and all that kind of stuff, so I can understand these things a little bit better. But anyways, there exists an efficient algorithm to encode n chunks of data, the data 0 to data n minus 1. The chunks can have any size into 2n chunks. So you're encoding n chunks of data of any size into 2n chunks, such that any n of those chunks suffice to reconstruct the full data. Okay? Does that make sense? We're not getting too complicated yet, so we'll keep going. The algorithm is as follows. Okay? Compute the polynomial p, where p0 equals d0, p1 equals d1, I guess so forth, where p to the n minus 1 equals d to the n minus 1. This polynomial is guaranteed to have degree less than n. Then evaluate this polynomial at 2n positions. The original n, okay, but also p of n and then p of n, and all the way up to p of 2n minus 1 to get 2n evaluations. Okay. So this is the background of data. So now what I love about these papers is because I've actually been meaning to read this exact same paper for a very long time, and I've not done it. So I'm actually going to open this, because this paper I will review on the page, and I've been meaning it for a very long time. But this is the first time I've ever actually kind of like read into data availability sampling. So I love papers because it kind of gives you a background on all the things you need to know, and then you can kind of get into like what's new and what's revolutionary about this specific paper. Let's see. Okay, we now use an important property of polynomials. Given a polynomial of degree less than n, any n evaluations of the polynomial at n different points can be used to reconstruct the polynomial and hence the original data. Okay, so that's just something we are that has been proven. I'm sure there's a proof for that. We know that that's a property of polynomials. So, moving on. Hence, if we consider the collection of 2n evaluations of this polynomial at the values 0 to 2n minus 1, we can see that any n of them can be used to reconstruct. You're gonna have to show me. You're gonna have to show me this. Oh gosh, you can see that any n of them can be used to reconstruct the polynomial, and from there reconstruct the original data. So you're just trying to make sure you could always, instead of having to download the entire data, reconstruct the original data with not having all the points of data. Anyways, note that the above description is simplified for X position. To make it possible to use fast Fourier transforms to do the above operations in n times log n time, powers of some root of unity, w, are used as evaluation points instead of integers. Oh gosh, okay, and then we have to get into fast Fourier transforms, which above my level currently, so we're going to stick to what we are at now. What does this give us? It gives us a way to turn 50% availability into 100% availability. This matters because checking for 50% availability is vastly easier than checking for 100% avail- for 100% availability. Checking for 100% availability can only be done by downloading all the data, and that kind of makes sense because even if you wanted to download 99% of the data, you would never actually know if that last 1% was available or if it was missing. So you'd have to download all of it. But with this, with this math, I guess you'd be able, and I think the whole point of this is you need to do multiple nodes need to be doing this, and then probability states, probabilistically, with a few random sample checks. Okay, let's see. Let's keep reading instead of me just ranting. Even if you download the entire 9% data, that's exactly what I said. Okay, but checking for 50% availability can be done probabilistically with only a few random sample checks. This is the key trick that allows us to do scalable data availability validation. And so the idea is that we're working to, instead of one person, like the whole Bitcoin idea is where like you run a node and you verify everything and you make sure everything's there, which is great. Bitcoin shows that it's possible. What I think Ethereum is trying to do now is say, hey, we can work together as a community and get this done as well. And I think Near is doing a similar way of doing things in their blockchain, although it's a bit different because you don't want to. Anyways, I'm going to go there. Kate commitment. So I do want to look into Kate commitments. The Kate commitments is a lot more math, and so it's going to be confusing when I go through it. But I am going to go through it probably on Monday or Tuesday, and it's going to be like an introduction. But it's something that I want to make sure I understand better, and so I want to go through on this page on the channel as well. So a K commitment is a fixed size elliptic curve pairing based commitment. So you have your commitment of P to a polynomial P. So you're committing to P, which has the property that for any evaluation point Z, okay, so the polynomial you're evaluating at Z equals A, for some A, you can provide an opening proof, okay? Another elliptic curve point Q, where a verifier given the commitment to the polynomial P and they're given the elliptic curve point Q can be convinced that the point evaluated at Z actually does equal A. Oh my gosh. Math is hard. I love it though. I love it. This is very useful technology for us because it means that if we generate the commitment for the polynomial and use that to represent the data, and we generate openings for each of the 2n outputs, then the openings become self-verifying. As long as the header is well formatted, there's no way for a shard data block to be invalid. It can only be unavailable. This key property allows us to completely avoid the need for any fraud proofs. Okay, so yes, by having validity proofs, I guess you don't need fraud proofs because you're unable to have fraud because either something is valid and it's there, or it is invalid and unavailable. There'd be no way to actually use the invalid state because it wouldn't show up, I guess. Unlike in ETH1, we can no longer simply publish all shard data to the same shared PDP network. Because like in Ethereum 1 or in Bitcoin, like I said, you run a node, you get all the data yourself and you know you have all the data. This is because a node that is on that network would be forced to download all of that data, removing the benefits from sharding. The whole idea of sharding is that you can run maybe the network for what you need and maybe a bit more, and everyone does that. We'll all be okay, but you don't need to download all the data for the network. With the above parameters, the amount of data broadcasted would be 256 gigabytes per block. Kilobytes per block. On average, assuming an EIP 1559-like mechanism times 64 shards divided by 12 seconds per block would equal 1.33 megabytes per second, around 11. Wait. Megabytes. Wait, are these different things? Yo, I'm sorry. I've never actually seen. I feel like I want to Google that and be like, why are these written out differently? That is so. Or maybe it's saying it's gonna be around this much once you have the PDP overhead. But it is expected to expand over time with more shards and a larger block size. Are we saying we're gonna have more than 61 shards eventually? Oh, geez, I don't know. And a larger block size. Okay, cool. Larger block size sounds interesting as well. Although, I guess over time, technology will advance to allow for a larger block size regardless. Instead, we use a subnet architecture where there are multiple PDP networks and each node is only usually on a few of them at a time. Okay? We have three kinds of subnets. Okay, we have a shard block. We have shard block subnets or horizontal subnets. We have same index subnets or vertical subnets. And then the shard data header subnet or the global subnet. Okay? So let's try and look at this in one little diagram. Oh, gosh. Always happens. I sit down, I start yawning. Anyways, let's get going. When a shard data block is published, the header is published on the global subnet, okay? So when a shard data block is published, the header for that block is published on the shard data header subnet. And the block, okay, so the header is on the global subnet. The block is published on the horizontal subnet, the block subnet, corresponding to the shard ID. Okay. For each I in 0 to samples per block -1, the ith set of evaluations, points per sample times I to point per sample times I plus 1 minus 1, I plus 1, okay, that minus 1, is published on vertical subnet. For each I, the I set of it. So the evaluations are on the vertical subnets. So here you have your vertical subnet at the top, where you get your evaluations. The horizontal subnets are all your blocks going down the left-hand side of the graph. And the shard data header and the global subnet, I don't see it on the graph, but yeah. Note, a possible extension is to shuffle which vertical subnet corresponds to which sample index in each slot so as to balance the load of the different shards in the case of blocks of different sizes. In practice, there would be 2,048 horizontal subnets instead of 64 to allow for one horizontal subnet per shard or slot combo in each epoch. So it's not just the shard once, but you're doing it for each shard slot combo in each epoch. This is done to ensure that each validator can join a single subnet where they will only receive the block corresponding to the committee that they were assigned to. Okay, each validator must join the following subnet. So here we go. You'd have to join the global subnet. Okay, so you just get the headers of all the shards so you can start looking at where you need to go. You get the horizontal subnet corresponding to the shard slot combo that they were specifically assigned to. So they're already, instead of having all the data, you're getting all the headers, and then you're getting your assignment for your validator, which will be on the horizontal subnet, which is the block, right? So you just know the block and slot you're assigned to. And then the vertical subnets corresponding, remember the vertical subnets are going to be the evaluations. So you get the vertical subnets corresponding to indices that they are assigned to. So each validator computes this for themselves using a private seed, I guess, so that others wouldn't know exactly what data you're going to be validating beforehand. Only the specific validator would know what data they're going to be validating. I would assume that's the case there. So the index calculation algorithm, this is going to be fun to read through. But let's read through it because, the only way to understand these things is to just read through them and try and understand at least 1% of it, and then next time 5% of it, and then one day I might understand like 95% of it. But anyways, sample indices returns the vertical shards that a validator should make sure to be in during a given slot based on their private seed. The code below can be run self-contained. So from hashlib import SHA-256, hashing algorithm, you're importing it from the hashing library. That much I understand. Awesome. You're going to have a function to hash certain value, and it's going to return a hash of that value. .digest, I don't know, man. Maybe it's just going to return it in a nice little format that'll make it look good for us. Okay, so samples per block, fast shuffling samples, slow shuffling samples, slow shuffling period, offset, the bytes, 32 equals none, list equals integer none. So these are all the variables we're going to need for the, I guess, for the program, for the function, for the code. And all these data are just the parameters from up here, right? The same ones we looked at previously: shard count, points per sample, modulus, whatever. The offset is a new variable that wasn't there previously. The bytes 32 and all that, but we'll look in here and we'll see where that gets to. So you have a function, get delta, and then your seed, okay, is bytes 32. I don't know Python that well, so bear with me. Okay, I know more Viper than I do Python, and so I'm using my Viper knowledge. But okay, I'm pretty sure this is in Python. I don't even know. It looks like I just know, like, Anyways, adjusted slot is an integer. Positions will be an integer. I guess you're just taking Adam. I don't know. Okay, to do. Consider replacing with an NPC-friendly function like, I don't even know what NPC function this is, but I did a little bit of research into NPC with my time at HashCloak, and so I think the idea of NPC is super cool, but I don't know enough about it to even start to comment on how that would improve the function aside from more robustness or something like that. But anyways, you're getting your delta to start with, so maybe the point is you're getting the delta with an NPC function instead of one person running the function. Adjust slot 2 bytes 32 little position int from bytes. So maybe that's like this, the new index integer from bytes. So you're putting from bytes to an integer. You're taking from the seed. I don't even know. Samples per block. Modulus samples per block. Your position is okay. Yeah, I don't know, man. Anyways, you call the function get delta, and you're going to put in those parameters, and it's going to return to you your position and a new index. The new index for Anyways, then you have the next function, sample helper. Sorry, takes in the same seed that you have, I guess, I suppose. The slot, which would be an integer. Okay, the positions, integer, and then the list, integer. Okay, output equals none times position adjusted slot equals slot plus offset. See, I don't know enough about what is happening to know what is happening in the code. Fast indices, offset, period, show shuffling, period. Man, I don't know what any of this stuff is talking about. The intended behavior is that there are two types of indices. Okay, why are there two types of indices? Fast shuffling indices and show shuffling. I get that there's two, but why? One fast shuffling index changes every slot. Okay, I get that, I suppose. So you have your fast indices and your slow indices, and for both of these, you're going to call the sample helper function with your secret seed here. Your slot is an integer here, right? And then your fast shuffling samples as your position, I suppose. But the point is, why? The one slow shuffling index changes every slow shuffling period. So you have something changing. Okay. The slow shuffling indices are chosen from a public seed. This allows easy discoverability of nodes that are guaranteed to be on particular subnets. Okay. So your fast shuffling is most of them, the nodes, but they have a longer period of time where certain nodes don't shuffle, I suppose, so that you are able to know where those nodes are because they're not shuffling as often, allowing for node discoverability. So you know, because you need to connect to a node on every subnet, it seems, right? Each validator must join, all three subnets, but not all the data on all the subnets. Only all the data on the first global subnet. Okay. Shared data commitment structure. Okay. Class, shared data commitment. Okay, gosh, we're looking at containers now. This is why I hated going through like React and JavaScript. We started talking about classes and containers. I was like, what are you talking about? Because every programming language names all these things differently, and so that is definitely. I cannot wait till we have like one global programming language. Not that it would always be the same, but just that like I feel like there's usually one programming language, all the same syntax, and then like it has like like JavaScript Lite, JavaScript TypeScript, JavaScript for like Rust, assembly script, like just create all different types of the same language so that we can all talk in the same lingo to each other. But anyways, signature, okay, length proof equals the BLS public key. Length is uint64, and the commitment is the BLS public key. Signatures and signer related data to be determined. Okay. Publishing. Note that while we can reasonably expect the publisher of a shard data block to be on the horizontal subnet of the desired shard, they are not going to be on all the vertical shards. That is reasonable. So to solve this, we use a two-step broadcasting mechanism. Okay. Every block has an associated committee that are all on that horizontal shard. Okay. The committee members, around 128 of them. I think that's around like the minimum amount needed for like maximum security. I was reading like the Gasper paper or something like that. Anyways, the committee members receive the block. Okay. Each of the committee members, okay, asks each of their peers. Conservatively, it's going to be 128 times 10, okay, what vertical subnets they are in. So I'm assuming that you're going to get 16, the amount of questions you answer, you're going to get those amount of responses times 16. I would assume because each peer is going to respond with 16 messages with the 16 vertical subnets they are a part of. They broadcast the appropriate samples to each peer. So if I have data that someone needs, I'll broadcast a sample, and that should kind of make sure everyone's getting what's needed. So each peer that receives a valid sample broadcasts it to their subnet. Okay. This broadcasts an expected 20,480 samples, enough to, in expectation, provide around 14 times the number of samples needed to reconstruct the block. So that could potentially mean that you don't need to, like, you could be sending a bit less data or less messages, but I mean, you're always playing with fire when you start, lowering all these numbers, right? Including inefficiency from double covering an index, you need around 69.3% of a block, or around 1,419 samples. This provides a large safety margin and ensures the block actually does get broadcasted. So I think what they're saying here, right, you're broadcasting 20,000, but you only really need a minimum of 1,400, whatever. But they're saying that, that's the bare minimum. It wouldn't be as safe and whatnot. So obviously, instead of being unsure if a block will get broadcasted, we're going to make sure the block gets broadcasted, and we're going to have a huge safety margin, and we're going to make sure it works out without having to still download all the data, which is just, and over time, maybe this number can be dropped, and, maybe 14 times is a bit much, and over time we can get down maybe to 11 times, 6 times. You don't want to overpay too much for security, but better to overpay for security and not get hacked than underpay for security and then, GG. Okay. We're going through technical details of fast Fourier transforms. The first time I heard about these was from the Stark at Home series with Dr. Ben Sasson, Dr. Eli Ben Sasson. Yeah, some good information there, and excited to dig into it in an actual paper now. I definitely agree that like going through really complicated topics in a video format is great to kind of hear it and hear the way words are supposed to be said and hear the way things are supposed to be done. But it's kind of hard because once you miss one little thing, you're completely gone. Where here I can kind of look over the same data over and over again and try to really kind of soak up as much as I can here. So that is what I shall do. Okay, so to make the erasure coding efficient, we find a root of unity with order 2n. Oh gosh. equals points per sample times samples per block. That is, we find a W such that W to the power of n equals 1. In modular arithmetic modulo, the modulus in the config above. But W to the K does not equal 1 for any K where, K is between or is greater than or equal to 1 but less than n. So K is a positive number greater or equal to 1, okay, and less than n. But what's our n? Sorry. Is n just the number of nodes or yeah? So W, okay, so n's the number of nodes, let's say, I think, okay. Find a W such that W to the n equals 1. No, n is not the number of nodes. Anyways, we use W equals 5. Is that to the power of? So W equals this crazy number. So this crazy number to the power of n equals 1. And 2n equals points per sample times samples per block. Okay, let's see. So before we're using just 1 to 2n as our evaluation points. Now we're using powers of W in order of reverse bit representation. I need to watch some YouTube videos on reverse bit representation now, but we're using powers of W, which is here. So you have your function, which we're doing that reverse bit right here. So reverse bit order for bits. So if bits equals 0, return what the first return x times 2 for x in reverse bit order, bits minus 1, plus x times 2 plus 1 for x in reverse bit order, bits minus 1. Yeah, you're gonna have to give me an example, my friend. Here are the examples of outputs. I need to I should bring up, what I should do is try and pull up a coding terminal for some of these things and just run these things in a terminal and see if I can get them to run. Because I usually just read code and I have to try and run through code, but I should probably start doing that. Inputs with low values. So the value that would be used as an input to generate the exponents that will actually get used is log 2 32,768, which equals 50. Okay, anyways, if you call the function reverse bit order of bits just 1, you get return 0, right? So return the array, return the bits, return something. So, but you're returning 0, 1. Put 2 in, you get 0, 2, 1, 3. Put 3 in, you get 0, 4, 2, 6, 1, 5, 3, 7. That's scary, huh? You're getting all the even numbers on one side, the odd numbers on the other side. I'm sure there's some pattern here somewhere. If you put reverse bit order 4, so the first one seems to always be an index of 0, and then 8, 4, 12, 2, 10, 6, 14, and 1 up. Okay. So reverse bit order has a neat property that any power of 2 aligned subnet. Another way to think of this, any power of 2 aligned subset. Another way to think of this, any subset that would form a clean subtree if the list were put into a Merkle tree, okay, is a subgroup or a coset of a subgroup of the multiplicative group of powers of W. I sort of understand why that's efficient and that's why that is helpful. This makes it very mathematically clean to use a fast Fourier transform to extend the original data at endpoints into the extended data, okay, to endpoints. You're taking the data you need to verify and then creating 2 endpoints so that nodes can sample from those points randomly, or I'm not sure if it's randomly, but they sample from those points, and then you only need 50% or whatever of them, okay? Particularly note that the original data, which goes in the first half of the evaluation points, neatly falls into the powers of W, i.e. the powers of W squared, which is a subgroup, and so a fast Fourier transform can be applied directly. Oh, does this mean that you just put the data in of 1 and so you get 2 points? You put the data in of 2 and you get 2n of 4 points. You put the data in of 3. Oh, but it's not really 6 points anymore, is it? You're kind of getting 7 points. But let's see. How many points do you get here? Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. No, it becomes like 12. 9, 10, 11. I don't even know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're definitely going up by, W to the power of 2. Two, 4, 8, 16. Interesting. Okay. 2 to the power of 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. But, anyways, I'm quite lost. I'm trying to get back to the reading. Prove that any particular continuous subrange is full of zeros. Okay? For this, we compute a polynomial z of x minus w. I actually don't. What, the reverse of I? Reverse bits of I times what? Times w minus, x minus w to the reverse of j. But if you're just going I and then j, I wonder why there's these dots here. For this, we compute a polynomial z and provide a commitment to Q of X equals P of X over Q Z of X. The verifier can generate the G2 representation of Z and do a pairing check to verify. I need to start reviewing more of my discrete mathematics, apparently. My gosh. I mean, obviously I do. It's just, without I know I was in university for this, but like, so boring. But the good part about university is that you kind of have a streamlined process of going through all this stuff. But anyways, yeah, I don't understand any of this. I'm not even gonna, like, I'll read it though. I think one of the best ways to understand math is just read math, and then after a while you just kind of start going through the math in real time, and you're like, oh, that kind of makes sense. And then you start programming the math. Programming the math makes it easier as well, because you can like visualize the math a little bit, and like you can see it breaking right in front of you, which is, I think, helpful. But yeah. Okay, the verifier can generate the G position of Z and do a pairing check to verify E. Q, compute Z equals E, completion of P. Oh man, note the powers of W can be viewed as at most 2 times log 2 j minus 1 subtrees ij minus 1 subtrees log 2 j minus 1 I if j equals n over 2. Man, why are you confusing those math? Okay, making it easy to compute Q of X. Z of X2 will be a product of a few x to the power of 2k minus w to the power of 2k times r terms, making it and the commitment to it easy to calculate. Fast Fourier transforms hurt my brain. I'm just going to say that right there. This is the last little part of the article, though, and then I'm going to go, like, just try and forget everything I just read because my brain's already numb. One important point that must be stressed in this data availability scheme is that the shard block data should be viewed as natively being a list of integers in the range 0 to modulus minus 1. This is a departure from ETH1 and indeed almost all other blockchains except perhaps IOTA, which uses ternary, which tend to view data as natively being bytes. So I guess what we're saying here is that since the data isn't being held by everyone, it can't be just natively accessed by everyone. So you can't just load the data the way whatever state it's in. All data is, I guess, going to be in bytes so that you can run calculations on it and all this math. And then I guess you're gonna take the data when you read the data, right? You're reading the bytes, and I guess probabilistically you'll be getting the correct data. Is the way I understand all of this, and the math here is to ensure that the data is actually there, it's actually available, and the data is correct in a safe, secure way. One important point that must be addressed, okay, that is, for example, modulus equals 13. So the set 5, 10, 2, 7, 12, 4, 9, 1 would be admissible data. But 1, 8, 15, 6, 13, 4, 11, 2 is not, okay? Because your modulus equals 13, so 13 and 15 are invalid elements, okay? This should be viewed philosophically similarly to how, for example, okay, this is valid hexadecimal, but this is not, okay? I mean, I've never seen hexad 0x70 BDGHI. Yeah, it doesn't look right. Again, this part doesn't look right. Anyways, the data availability check that we use is natively built around modular arithmetic. And so the data it verifies availability of is in a format of a list of integers in the range of 0 all the way up to modulus minus 1. And now with this example, I like it because you could see why it's modulus minus 1 is because if you have some data in here that's at modulus or above, it will be invalid. So it needs to be modulus minus 1. The main challenge here is that serialization and networking use bytes. And so there is a disconnect of formats between serialization, networking, and the data availability scheme, which uses points. Okay. But I thought the whole point is that we were saying that. Sorry, I didn't even read this. A lot of property is needed because for EIP purposes, we need to enforce the size of a shard block in such a way that it can be verified from the shard header. For this, we use the application-specific snark summarized above to prove that the data. So there's an application-specific snark summarized above to prove the data outside the range is zeros, so no one needs to try to propagate or download those coordinates. I need to I want to understand this. I do, but I do not. we're gonna go there. Okay, the 32-byte blob, 0x, a bunch of f's, is valid bytes, but is not a valid point because points must be lower than the modulus, which is a prime number somewhere between 2 to the power of 256 and 2 to the power of 54 and 2 to the power of 255. Very interesting. To deal with this disconnect, we encode every point as 32 bytes in little endian, okay? But we add to every object that contains a point a validity condition that requires the point to be less than the modulus. So you take the point, convert it to bytes, and then say, hey, you're in bytes now, and you're valid bytes, okay, but you're valid for bytes, but you also need to make sure to be valid that you are less than the modulus. Objects that contain points that are out of range are effectively ignored and treated as non-existent, as though they had never been received by the client. So now if your client receives a point that's outside of that modulus, it can just know not to accept it as valid because it's not within the range, the bounds that you're using. Note that at the application layer, applications usually prefer to use bytes. How to convert a list of points into bytes is so how to do so is an application layer choice. A natural default is to just take x mod 256 to the power of 31, only looking at the bottom 31 bytes of every point. So that's the end of the article. I probably understood like less than 75% of that, probably like half of that. A lot of that was quite complicated, but I did learn a lot more about phase 2, which is exciting. Slow shuffling indices, slow shuffling samples, slow. Maybe the point was here, how you have like fast shuffling samples, and then you have, this kind of confused me, right? Because why does this say number of sample indices, and then here it says slow shuffling indices, great, but then here it says fast shuffling samples. And so my brain is like, okay, should this say slow shuffling samples? I think it should. So I assume the comment here is saying that slow shuffling indices should actually say slow shuffling samples. Very interesting. I think that this person is part of the dystopian labs. Sorry, I'm so bad at keeping, I can't remember who this is. Oops. Twitter. Yeah. Oh no. ETH2 Research and Development, but not the head of, that's someone different. But very cool. I try and follow most people that are doing ETH2 research development in general. So yeah, I kind of knew I was reading what them. I knew I was following them. But yeah, I think that would be. I like the post. Good post. I want to try and keep up with it. So I do have MyHackMD. I'm not even sure if MyHackMD stuff is still even there or like available. But anyways, if you have any questions, concerns, comments, I'm probably not the correct person to ask. But if you go to ETH Research, and you know what, I will link ETH Research in these video notes. Forum, because I'm gonna start doing a weekly stream where I start poking into the ETH Research and looking through a lot of this comment, like, a day ago. There's so much stuff happening every week, and I just haven't had much time to poke in and kind of read through it all. So what I want to start doing is, let's log back in. I haven't even been on the forums in a while. Let's log in. And so the idea is maybe every Sunday evening. That's kind of what I have on my board right now. So every Sunday evening, my plan, or Monday, is to go live and just have fun. That's what I want to do at Sundays. I want to, this dirt simple withdrawal contract. I read to that one of these days. It was pretty interesting. Roll-ups on a data sharded ETH2. Probably very interesting to read through it. 0 replies so far. So again, would love to kind of get more into this type of stuff, but this is more just me having some fun, jumping into the forums and learning a bit. So I'm going to be live streaming that hopefully every Sunday every Sunday evening. And so yeah, if you learned anything new, I hope you did learn something new in this live stream. It's only an hour. Definitely read the paper yourself. Definitely pop into ETH Research yourself. I am just a random individual who enjoys learning about ETH2. I am no one special, and so if I can go through the papers and learn a little bit, so can you. So yeah, hope you all have a wonderful weekend. I won't be streaming this weekend. I'm kind of heading back to visit my mom, visit my family this weekend, and so I'll be back at it on Monday. I'm looking forward to doing this on Monday more. So, maybe Sunday night. I might do Sunday night. I might go through ETH research. But see everyone. Have a wonderful weekend. Chloe.